Okay, welcome back, everybody. So, yesterday do we have class on Monday? That's a good question, actually. Let me check. Let me actually check UMD's schedule because I don't know. Let's see. Uh, let's see. UMD academic calendar 2022, I believe, is the year. Okay. No, I guess actually summer is on the previous year's calendar, right? So I guess this would be 2021. Uh, Weirdly enough, I think that's how that works. Um, so let's see here. Yep, I need to go back. Oh, always confusing. So let's see here. Summer 2022, no class the 20th. That is correct. So actually, I didn't know that until just now. So no, I'll put that into chat. Okay. So your second uh, I should say or not your second, your midterm. I'm going to post later today. It might be like tonight, and you'll have a couple of days to do it. We'll say that it's due Monday, so this will give you plenty of time to get it done. I'll post an announcement when I do that, so you don't have to be constantly checking Elms or anything. You'll be able to see my announcement when I post that. So be looking for that. Okay. So anyway, last time oh, wait a minute. I was looking at the University of Minnesota Duluth. Oh my God. I think it's the same for UMD, but why is the schedule so hidden? Why is it so obfuscated here? But yeah, that's what I said is still true. So UMD's is also off. So yes, no lecture on Monday. Anyway, all right. So the spring mass systems we were looking at yesterday. This is from our original formulation of F equals ma. I thought of F as being composed of all these different forces, so gravitational force, spring force, the damping force, and any external forcing is equal to m times y double prime being the acceleration there. So of course, recasting this slightly by now, looking at, rather than the displacement from initial spring position, rather we look at the displacement from the resting spring position once the mass has already been attached. This gave us the following. A spring mass system could be modeled by the following second order differential equation. So this was m times h double prime plus c times h prime plus k times h is equal to this external forcing function, possibly. Okay, this is the most general possible spring mass system that we're going to talk about. Okay, so this is most general spring mass system. But what are all these quantities, right? M, C, and K are all constants, right? So M is the mass of the object in question. C is the damping coefficient. K is the spring constant. These are all constant. F is a forcing function, but we're only going to so we will only assume that if this forcing function is not 0, this thing will be in the form of like a cosine of something times t, right? A cosine of, we'll say, c t. I'll write it like this for now. Okay, this will be the only sort of forcing function that we allow ourselves to talk about here. Okay, and so either f is 0 or f is something like this. So because of this, right, I guess, you know, the thing that I'm really asking here is, at the end of the day, when you have interpreted some data that I've given you into this problem, okay, and you've put it in this form. So you found m, c, and k. Typically, right, you're given m, but not c and k. C and k are things you'd have to find through those relationships we mentioned yesterday. So you're given m, not c and k, but you're given enough info to figure out c and k. So once you have written this expression out, what is this? Well, this is a constant coefficient, linear, possibly non-homogeneous equation, but the worst that this forcing function can be is something like this. Okay. Well, what kind of thing, you know, is this? This is linear, constant coefficient, non-homogeneous, possibly. Second order equation. And so, what methods that I've learned allow me to solve any such problem? Right? Well, undetermined coefficients and key identities, right? Because f is not only in characteristic form, it's actually in a really simple characteristic form. So what this is saying is that undetermined coefficients and key identities will work for any of these problems. So it will work for all of these problems. So in terms of methods required, undetermined coefficients and key identities are the only thing that you need here. Okay. So that's that. All right. This is just kind of good to keep in the back of your head when, you know, you ask yourself. I give you one of these problems. This is an applications problem, so typically this manifests itself as a word problem. So you have some long-winded word problem, right? You are going to be setting up exactly this kind of equation. Worst case scenario, all of these things are non-zero, which means worst case scenario, you get a constant coefficient, linear, second order, non-homogeneous equation, which can be solved with undetermined coefficients or key identities. Because the forcing function is in characteristic form, it's actually in a very, very simple type of characteristic form. So that is just me trying to hammer in the fact that this is as bad as it gets for these problems. And a lot of times it's simpler than this. Okay, so let's see an example of one of those times. So I'm going to break this down into a couple cases. I'm not going to exhaustively do every case because I'm going to quickly just say, well, you know, if this thing is more general, then you would solve it in exactly the way we've solved all these sorts of equations when we encountered them before. But it makes sense to talk about some special cases here just to kind of familiarize you all with some of the terms. And you will have seen some of these things, but so it's nice to see them in this context because they'll be familiar to you. So the first case is going to be unforced, undamped motion. What does that refer to? So in this expression, c is the damping coefficient. This right-hand side function is called the forcing function, or this is the external force. So if this is unforced, undamped motion, this means that undamped means that the damping coefficient is 0. Unforced means that the right-hand side forcing function is also identically 0. Okay, and so what that leaves me with is an equation that looks like this. Now, A quick aside, sometimes you'll see both in the text book or the online notes and online if you're looking at other resources, notation like this, and you may have encountered this notation previously. So using dots instead of primes to denote derivatives with respect to t specifically. So, h dot is dh dt, it should be said. If you haven't encountered that notation before, that's what it means. This is like Newton notation. So Newton actually used this notation in when he was doing various physics problems in both Principia and a lot of his writings. Period. He used this notation frequently. Sometimes this notation gets used specifically for these problems. So the online notes typically uses either Leibniz notation DDT or prime, but sometimes for these problems you'll see this instead. So just don't get confused. That's the meaning behind this. Okay, and so unforced undamped equation looks like this. Right? It's just me looking at this general equation here and letting C be 0 and the external forcing be 0. So I'll write that here. Right? Unforced undamped means my external force function is identically 0. When I write that, it means 0 for all t, right? Not just 0 at some t. And then C is equal to 0. The damping coefficient is equal to 0. So this is what I get. Okay. Now I'm going to try to just completely generally solve this thing. Okay. So what's first step? Well, I always like the resulting characteristic polynomial to be monic, right? That means I want the leading coefficient to be 1. So divide through by m. This gives me h double prime plus k over m. I know my k's can look like h's sometimes. Forgive me. So h double prime plus k over m times h is equal to 0 is what I get. So what is the characteristic polynomial? This is a homogeneous, right? So this is now homogeneous. It's a homogeneous equation that's linear, second order. So I know exactly how to find the solution to this. So the characteristic polynomial is what? So p of z is z squared plus k over m, right? And so what are my roots here, right? Well, k, so m is a mass, spring constant is also non-negative, so this is typically a positive thing, which means this has complex roots, right? So the roots are z is equal to, it's a conjugate pair of roots, plus or minus I times, I'm going to write this as omega naught, where what is omega naught? Omega naught is the square root of k over m. All right. Now, of course, I didn't need to introduce this notation, but I'm going to because this has a name. Okay. So we'll talk a little bit about this, and I'm going to define a few terms here. But first of all, so I could have just written plus or minus I times square root of k over m. That's fine. But I'm going to give this the name omega naught. All right. So then a general solution is the following, right? So my roots are complex. They have real part 0. So what is this? This is h of t is c1 cosine of omega naught t plus c2 sine of omega naught t. All right. If I had initial conditions, so let's say that I had ICs that were h of, we'll initialize this at t equals 0, so we'll let h of 0 be h naught and h prime of 0 be h sub 1. If we impose those initial conditions, then we can actually get a unique solution. So imposing ICs, I get that h of t is equal to h naught cosine of omega naught t plus h sub 1 sine of omega naught t all over omega naught. Okay. So what kind of motion is this? So what kind of motion is this? Because remember, this is ultimately me tracking the displacement from resting position of this spring mass system, right? So I impart some initial data on it. So an initial position is indicated by this, right? That indicates an initial position that the spring mass object occupies. This indicates an initial velocity that it's imparted with, right? And then after that, I don't touch it. There's no forcing. It's undamped, so there's no damping coefficient or whatever. So then I just let it go. What kind of thing is going on here? What kind of motion is this? This is periodic. This is a periodic oscillation, and this is dictated by this single frequency omega naught. So this is a periodic oscillation determined by the frequency omega naught. This omega naught has a special name. This is called the natural frequency of the spring mass system. One of the reasons this is called the natural frequency is because what does omega naught depend on? Just K and M. K is the spring constant. M is the mass itself. So this is like an innate or like inherent quantity associated to any such spring mass system, right? So just directly, this depends on both the spring and the mass, right? Okay, so this is called the natural frequency. Omega naught is called the natural frequency of the system. Okay. So what are its units? So its units are like radians per second. Okay, that's not going to come into play too frequently, but those are the units for this thing. There's also what's called the cycle frequency. So let me go to another page. So the cycle frequency which has notation F naught. This cycle frequency is related to the natural frequency by the following relationship. So 2 pi times the cycle frequency is equal to the natural frequency. So i.e. the cycle frequency is 1 over 2 pi times the natural frequency. Okay. So this has units of cycles per second, right? So think what you're doing here, right? You're normalizing by 2 pi, so it's telling you how many cycles per second rather than how many radians per second, right? All right. And so there's another quantity that I define in the following way, or is related to both of these in this following way. T naught is the natural period This is the natural period of the system, and it satisfies in the following, that f naught is equal to 1 over the natural period. So I'll write it like this. So that the natural period is 1 over the cycle frequency f naught. Okay. So this natural period is a time measurement. This is in terms of seconds, right? The natural period, of course, note that h of t plus the natural period is h of t for all t in the spring mass system. So this natural period is the thing that defines the periodic motion here, right? That once you have completed this many seconds, right, you are back to where you started for that cycle. Okay. So there are some, if you're looking in other places, there are some differences in some of this terminology. I'm using the same terminology that the online notes uses, just to be consistent. So all the notation I use is going to match up with the online notes. But in other textbooks, and engineering textbooks and physics textbooks, sometimes you'll hear omega naught called the angular frequency rather than the natural frequency. So so just be aware of that. If you hear people talking about angular frequency for these problems, that's omega naught. That's our natural frequency. Now, ultimately, you might ask yourself, like, why do I need to do any of this, right? I could, right, just solve this. Like, I know what these numbers, I'm going to be given these numbers, or I'm going to be able to find these numbers that I can actually solve this. So why do I need to know all this? This is just going to help you interpret what it is that this tells you, right? When you solve this thing, you might be asked, like, to actually describe the motion that's taking place. And so this is going to help you with that. Now, let's go back and look at this expression. Right, so here's h of t, and I'm just going to write that again. I'm just going to copy this down here. Okay, so h naught cosine of omega naught t plus h sub 1 sine of omega naught t over omega naught. So here's the thing. I told you that this is periodic motion. It's totally determined by this omega naught frequency. And so this is some, kind of oscillatory sinusoidal thing. But you might look at this and say, well, I believe that's the case, and I know that combinations of cosine and sine like this work out to be that way. But it's a little hard just looking at this to figure out what's going on, right? So if I'm claiming, right, that this satisfies some periodic thing, then I'm claiming that if I were to plot this, it looks something like this. Right? I'm claiming it looks something like that. All right? And maybe if we go into negative t, right, it looks something like that, okay? Well, whenever I have a thing whose motion looks like this, there's some quantities associated with this that I'm interested in, right? Of course, we've been talking about period, frequency, all these kinds of things, and you can actually note some of these things, right? Like there is a copy of where I start. If I start here, I go back to there. Or like if I start here, it's here when I first repeat the value, right? So so there's that. That's one thing. The other thing, though, is like if you were trying to describe to me exactly the behavior here, the easiest thing you would do is say, well, I want to find this. I want to find the number that tells me what these values are. Well, what's that number called? All right, someone knows that, I'm sure. What's that number called? The number that tells me, like, how big the hills are, how low the valleys are. What number is that? Well, this is the amplitude, right? So this is the amplitude that I'm looking for. Now, I drew this thing. If this is a cosine, this is, if this thing is a cosine, it's at 0. But of course, I could have shifted this thing slightly so that this also indicates periodic motion. Yeah, something like this. But it's not. Oh, I drew it off the page. There we go. And of course, I could have shifted any way I wanted to here. So it doesn't have to look exactly like this, but this also indicates this periodic motion like this. In either case, looking in this form, it's not immediately clear how to match up these quantities with, say, the amplitude, or how to match up these quantities with whether this thing has been moved to the left or to the right, right? And so in order to do that, I want to put h of t into what is called phase amplitude form. What is phase amplitude form, or amplitude phase form? This is writing h of t as a, an amplitude, times cosine of omega naught t minus phi, where a is the amplitude, so a is positive, and a is the amplitude, and phi is some angular value contained in the half open interval 0 to 2 pi. This is the phase. Okay. So I want to put this form, or even better, if I go all the way back to the description of this in terms of generic constants C1 and C2, I want to put this linear combination into this form. Can I do that? Can I rewrite this as just a times cosine? Rather than having C1 times cosine plus C2 times sine, I want to write both of these things combined as some a times just cosine, a single term. Can I do that? The answer is yes, and I want to use cosine addition formula to do this. So by the cosine addition formula, I can say rewrite this expression in the following way. So I'm going to use cosine addition formula applied to this thing. If you don't remember the cosine addition formula, you can look it up. Okay, you don't really need to remember it for this course, but this is what I'm using here. This is a cosine of phi cosine of omega t, or omega naught t, plus a sine phi sine of omega naught t. But then combine this with the form, but also our original form of h was C1 cosine of omega naught t plus C2 sine of omega naught t. So really, going to phase amplitude form, which is this thing, a cosine of omega naught t minus, sorry, not delta, phi, going from here to here just has this single intermediate step of the cosine addition formula. i.e., this works so long as C1 is a cosine phi and C2 is a sine phi. But you've seen this before, right? What is this? this is just polar coordinates, right? So another way of writing this is that A is the square root of c1 squared plus c2 squared, right? And cosine of phi is c1 over A, and sine phi is c2 over A. Or another way of writing this is that tan phi is c2 over c1. That's another way of writing it. What this means is that A phi are just the polar coordinates of c1, c2. Okay, so another way of interpreting what is being done here and rewriting this as phase amplitude form is just applying polar coordinates to those arbitrary constants, right, that parameterize the general solution. Okay, so that's what's being done here. Okay, so let's do a quick example of this. So, example. A mass of 10 grams stretches a spring 5 centimeters when at rest. At t equals 0, the mass is set in motion from 2.5 centimeters below its rest position with a downward velocity of 35 centimeters per second. Let's neglect damping and external forces. So this is an example of undamped, unforced motion. Okay, so 3 questions. 1, what is the displacement of the mass as a function of time? This is displacement from rest position. So what is the displacement of the mass as a function of time? Secondly, what are the amplitude, phase, frequency, and period of the motion? And lastly, at what positive time does the mass first pass through its rest position? Okay, so 3 separate questions that we aim to solve. Really, 2 and 3 follow from 1, so if we can find the form that this thing takes, then we can answer 2 and 3 pretty straightforwardly. So our first problem is to actually set this thing up properly, right? So first of all, m is equal to 10 grams. Okay, so that's the first bit of info I give. And I'm told that this mass of 10 grams stretches a spring 5 centimeters when at rest. This is the info that's going to allow me to find K. So we had a relationship between the displacement and K, right? This came from Hooke's law. So recall that m times g is equal to K times the absolute value of y sub r minus y naught. The way to remember this is that this is K times displacement from rest, right? So displacement from initial, I should say. Remember, initial position for the spring was, you imagine the spring being attached, say to the ceiling, and you hadn't put the weight on yet. Right, you hadn't put the mass on the spring. So once you put the mass on the spring and it comes to a rest, that's the rest position. Okay, so that amount that this gets stretched, right, from initial, before I've attached it, to rest position, that's exactly this thing. So I am looking for K. I have M, that's 10. I know what G is. Okay, so I know exactly what G is, and I know I'm given this displacement. Okay, so then what I get from this is that 10 times G. Which units for G should I use here? I'm given centimeters here, so I should use 980 centimeters per second squared. So this is 10 times 980 centimeters per second squared. Right, so G is equal to, so this is 10 grams, I don't want to confuse you. G is the gravitational constant, so this is 980 centimeters per second squared. So this is 10 times 980 is equal to K times this displacement. Stretches a spring 5 centimeters, so this is K times 5. So then K is equal to 10 times 980 over 5, which 10 times 980 over 5 is just, so this is just 2 times 980 here. I can leave this for now as just 10 times 980 over 5 before I simplify anything, because maybe this will get nicer here in a second. Okay. So K is 10 times 980 over 5. That's our spring constant. So setting up this equation, again, this is, I'm neglecting damping, I'm neglecting the external forces. So this is an unforced, undamped equation. So the proper form this takes is m times h double prime plus k times h is equal to 0. So that is, m is 10, so this is 10 times h double prime plus k is 10 times 980 over 5 times h is equal to 0. And so dividing through by 10, this is h double prime plus 980 over 5 times h is equal to 0. Okay, simplifying that, 980 divided by 5 is actually 196, and so the equation henceforth I'm trying to solve is h double prime plus 196h is equal to 0. Alright, so there's my setup. These problems are in two parts, right? So the part that requires the new knowledge, the stuff we've been doing since yesterday, is the setting up of the problem. But once you set up the problem, the worst it could possibly be is a second order linear constant coefficient non-homogeneous equation with a forcing function that's in characteristic form. So worst case scenario, you got to use key identities or undetermined coefficients, right? It's setting it up that requires this new stuff. But once you find C and K and set that thing up, depending on all the other info you're given. Then you've reduced your problem to something that we did earlier in chapter 2, right, when we first talked about non-homogeneous equations. Okay. All right, so this is the equation we're solving. Let me rewrite that. So the equation is h double prime plus 196h is equal to 0. Now, this is a second order homogeneous equation. Characteristic polynomial is z squared plus 196. All right, well, this tells me, so this has roots. Z is plus or minus 14i. It's square root of 196i. So this is plus or minus square root of 196 is 14. So this is plus or minus 14i, or I times 14. Maybe how the textbook would write it. And so what do I get here? This implies that omega naught, my natural frequency as I was calling it before, is actually 14. Okay. Therefore, general solution to this equation is h of t is c1 cosine of 14t plus c2 sine of 14t. All right, there's my general solution. Okay. Now I can actually solve for C1 and C2 here because I was given more than just the info to set up that equation. Let's go back here. So this first sentence told me enough to set up the equation. This first sentence, a mass of 10 grams, so here's my m is 10 grams, stretches a spring 5 centimeters when it rests. That gives me the displacement, which allows me to find k. That's all I needed to set this up and then solve the equation. Okay, this thing. All right, so then I was told more stuff, though, right? So at t equals 0, the mass is set in motion from 2.5 centimeters below its rest position with a downward velocity of 35 centimeters per second. Okay, so this second sentence becomes what? This second sentence becomes two initial conditions. The first one is h of 0 is equal to minus 2.5. That is, my mass is set in motion from 2.5 centimeters below its rest position. So h of 0 is minus 2.5. That's 2.5 centimeters below. All right. A downward velocity indicates that h prime of 0 is minus 35. So here's my initial conditions. I want to impose those here. So let's take the derivative. H prime of t is equal to, this is minus c1 sine, this is minus 14 c1 sine of 14t plus 14 c2 cosine of 14t. Imposing these initial conditions at t equals 0, I get minus 2.5 is equal to c1 times cosine of 0 plus c2 times sine of 0. And simultaneously, I get that minus 35 is equal to minus 14 c1 sine of 0 plus 14 c2 cosine of 0. Well, this first equation implies that c1 is equal to minus 2.5, which I'll write as minus 5/2. Okay, and the second equation implies that minus 35 is equal to 14 c2. Okay, which gives me that c2 is equal to minus 35 over 14. This is 7 times 5. This is 7 times 2. The 7's cancel, and I get minus 5 halves again. And so the unique solution to this equation is minus 5 halves cosine of 14t minus 5 halves sine of 14t. Okay, now we're happy with that, and of course in a lot of problems this is actually the end point, right? This is where we say we're completely happy because we have now found a unique solution to this differential equation, so hopefully we're able to answer all questions that are asked about it further. And that's true, but there's still a little bit of work that we have to do for this one specifically. Okay, so what is it that I want to know from this? Okay, let's go back to our question. So what's the displacement of the mass as a function of time? Yes, I have answered that. There it is. Okay, the next question, what are the amplitude, phase, frequency, and period of the motion? Well, I can say all of that stuff once I've put it in amplitude phase form. So I want to put this, so put into amplitude phase form. How do I do that? Remember, putting this in amplitude phase form is essentially the same as putting these numbers, so these coordinates, minus 5 halves, into polar coordinates. So if I want to put this into amplitude phase form, i.e., put minus 5 halves into polar coordinates. And those polar coordinates we will call a phi. What are the polar coordinates of minus 5 halves? Well, the polar coordinates are 5 root 2 over 2. And the angle is 5 pi over 4. Okay. And so another way of writing h is as follows. So h of t can be written as 5 root 2 over 2 times cosine of 14t minus 5 pi over 4. Remember, you didn't find another different unique solution, right? That wouldn't make any sense. That would contradict the solution being unique. This is exactly the same as that other solution. It's just a different form of it. Okay. We've just secretly used the cosine addition formula here. So there it is. What is the amplitude? It's 5 root 2 over 2. What is the phase? It's 5 pi over 4. What is the frequency? It's 14. And what is the period? This is pi over 7 seconds. Right, so the amplitude tells you a distance, that's centimeters. The phase is an angular measurement. The frequency is 14 radians per second, and the period is a time measurement. So these are all 4 of those quantities that I was asked to compute. If you wanted to very quickly sketch the solution, of course, you know how to do that from knowing the amplitude and phase alone, right? Like if you're just wanting to sketch this, right? Provide like a rough sketch of the behavior. Okay, so that answers, if I go back to this page where I ask these questions, what are the amplitude, phase, frequency, and period of the motion? I just answered those things. All right. How did I go from here to here? So how did I put this into polar coordinates in this way? Well, remember A is the square root of c1 squared plus c2 squared. But that, in this case, is the square root of minus 5 halves squared plus 5 halves squared. So this is 25 fourths plus 25 fourths. So that's the square root of 50 fourths, right? 50 is 2 times 25. So this is 5 root 2 over 2. How did I get the angle? Well, I get that tan phi is equal to C2 over C1. In this case, that's just 1. Okay. Now you can ask yourself, well, if tan phi is equal to 1, what are my options? Right. So my options are pi over 4. Right, that's an option. Is that the case? That would indicate C1 and C2 are two coordinates that are in the first quadrant. But is that the case? C1 is minus 5 halves, C2 is minus 5 halves, so no, that can't be it. Minus 5 halves is over here. So what angle is that? Oh, it's 5 pi over 4. Right? So this is some nice refresher course in solving trig equations, right? Trig equation typically has infinitely many solutions. So then a careful consideration of what quadrant your picture is what you need in order to pick out what angle you select there, right? So 5 pi over 4 is the answer. Okay, so that's how I got this in the first place, right? That's really all I need to do in order to transform this to amplitude phase form. So this answers that question. So then the last question I have, at what time, or what positive time, does the mass first pass through its rest position? Well, to answer the question of when it passes through its rest position, period, what is it that I'm being asked to do here? I'm being asked to solve for t when h of t is equal to 0. Notice that this is easier to do typically when h is in this form. So even if you weren't explicitly asked to put h in this form, sometimes it's more helpful to do that anyway, because this is a quantity where it's a lot clearer when this h is going to be 0. This amplitude is not going to contribute to that, so the only thing that matters for this thing to be 0 is this cosine has to be 0. But when is cosine 0? At integer multiples of pi over 2, right? So you have these odd integer multiples of pi over 2. So when is h equal to 0? This happens only when 14t minus 5 pi over 4 is equal to something like n pi plus pi over 2. Right? That's what's going on. And you're like, what is this? Right? Like, where did I get this from? This is where I know how cosine behaves, right? So I know how cosine acts when it comes to where its zeros are, right? The first cosine, or the first zero of cosine is at pi over 2, right? Then 3 pi over 2, and then 5 pi over 2, and so on. So it's these odd integer multiples of pi over 2. So another way of writing that is this. N pi plus pi over 2. If you're not convinced, you could say, oh, what about odd integer? So an odd number looks like 2n plus 1 times pi over 2. But hey, what is that? That is n pi, because 2 and 2 cancel, plus pi over 2 times 1. Right? Hey, there we go. So this is just another way of writing odd integer multiples of pi over 2. So this is what I get. Okay, so then 14t, of course, then is equal to n pi times, or plus pi over 2 plus 5 pi over 4. Okay, so this is 2 pi over 4, so this is 7 pi over 4. So this is n pi plus 7 pi over 4. Okay. So what is the first positive time here? So 14 is not going to contribute there. When is 14t positive? The smallest one that makes this happen is when n is equal to -1. So if n is equal to -1, this corresponds to 14t is equal to minus pi plus 7 pi over 4. So this is, minus 4 pi over 4. So this is like 3 pi over 4. So this 14t is equal to 3 pi over 4. Or t is equal to 3 pi over 56. Let me rewrite that better. So t is equal to 3 pi over 56. And so that is the first positive time t here that makes that work. How did I know that? Well, I just looked at this expression and said, okay, well, if n is equal to -2, this would be minus 8 pi over 4 plus 7 pi over 4. So that would be negative. So that would be a negative t. That's not what I want. So I want the smallest positive t for which this is the case. So then the next thing to try is n equals -1. And n equals -1 is, in fact, positive. Right? Any bigger n is a positive t that's larger than this. So 3 pi over 56 is the answer. So t equals 3 pi over 56 seconds is the first time this happens, the first positive time at which this thing passes through its rest position. Okay, so you see that all of those subsequent questions fell out of this phase amplitude form, which before I could write out the phase amplitude form, I had to actually solve and find the general solution anyway. So, your process here is basically the same as what you've been doing this whole time in Chapter 2. The only difference is that I had to work a little bit to actually set up this equation. Right? The equation itself was fairly simple, though. Okay, so that's an example of the unforced, undamped case. So I'm not going to go into exactly that bit of detail for all the other cases. I am going to go into detail for this next case just so that you can see all the terminology and stuff. But functionally, the way this will work will be a lot more straightforward because the resulting characteristic polynomial is a quadratic, and you know there's only 3 cases for how the roots are configured for that thing. Okay, and each of those cases is going to have a separate name and a separate implication. Okay, so the next thing I want to do is unforced but damped motion. So it's unforced, but it's damped. So in this case, my external forcing function is still identically 0. But now my damping coefficient is not 0, it's positive. So what is the equation for this? It's m times h double prime plus c times h prime plus k times h is equal to 0. Okay. Again, if I put this into normal form, what I get is h double prime plus c over m h prime plus k over m times h is equal to 0. The resulting characteristic polynomial is z squared plus c over mz plus k over m. Now, of course, there's 3 possibilities, right? That quadratic can have 2 distinct real roots, 1 real double root, or 2 complex roots in a conjugate pair. Okay, those are the only 3 possibilities for that thing. Now I'm going to write this completing the square. So let's complete the square. If I complete the square, I can rewrite this as z plus eta squared plus omega naught squared minus eta squared. Okay, where the damping rate eta is equal to c over 2m. This is called the damping rate, and the natural frequency omega naught is equal to the same thing it was equal to before, square root of k over m. So it turns out that I can complete the square and write it like this. Okay, so then in this case, there are three cases. We already knew that, but we can put these cases in terms of eta and omega naught. So there are three cases. Okay. So case one, when eta is strictly between 0 and the natural frequency, there's a conjugate pair of roots. So there's a conjugate pair of complex roots that are minus eta plus or minus I times omega sub eta, where omega sub eta is the square root of omega naught squared minus eta squared. Now, this is not something you're going to memorize typically. You're just going to know that the roots come in a conjugate pair in this case, and you're going to find those roots however you find them. The second case, if eta is equal to the natural frequency, we have a real double root. So there is one real double root that, if we list with multiplicity, is minus eta minus eta. And lastly, if eta is bigger than omega naught, then there are distinct real roots that are written as minus eta plus or minus the square root of eta squared minus omega naught squared. We have names for these cases. Okay. The first case is called the underdamped case. That's the case of complex roots in this situation. The second case is called the critically damped case. And the third case is called the overdamped case. Okay. Now, I want to stress that when you're doing these problems, typically, you're not going to wait until you've put it into this form with the eta and omega naught to actually say these things. You can immediately tell. So ultimately, you're going to have a differential equation in front of you. It's going to look like this. Here's your quadratic. These are going to be numbers, right? Once you found out what k and c are, you're given m. This is just some things. So this is z squared plus 2z plus 1, right? So these are actual numbers. You're going to find roots of those things. It's a quadratic, right? So that's a completely deterministic process for you. So you find the roots of those things. You're in one of these three cases. Two complex roots, one real double root, or two distinct real roots. And so in those cases, you can immediately say what it is. So two complex roots, it's underdamped. One real double root, it's critically damped. And if you have two distinct real roots, that's overdamped. Okay. So that is how you're going to classify this. All right. Now, of course, you can put each of these things into their own form. I'm not going to go into that amount of detail because it's not needed for the sort of things that you're going to be answering. But if you're interested in what each of these cases look like graphically, you should look at page 8. So pages 8 through like 10, I think. Really just page 8 is the main one. So page 8 in chapter 2, section 8 is what you should look at. So the online notes have really, really nice graphical representations of these things to let you know what it is that's going on here. Okay, so you can actually see some of these cases. Okay. Now, the forced, and here's an aside. How do I typically find C? So in the first case, we didn't have to find C because C was 0. So how do I typically find C? You're not going to be, the problem is not typically going to say, your spring mass system is in a medium that has damping coefficient C is equal to 2.78, right? Like that's not how it's going to work. So typically how it's going to work is that you will be told the magnitude of the damping force. There's a relationship that we saw yesterday, which is that the damping force is minus C times y prime or h prime as we've interpreted it here. Okay. And so the damping force is C times the magnitude of the damping force is C times the magnitude of the velocity of this system, right? And so typically you will be told the magnitude of the damping force at some speed magnitude of h prime is equal to something, right? So you use this relationship and this to find C. Okay, so maybe you're told that when the medium or when the mass thing is moving through the medium at a speed of whatever, right, 5 centimeters per second, the damping force exerts a force of 70 newtons or something on this thing. And from that, you would say, okay, 70 is equal to C times, 10 meters per second squared, whatever, right? That's how you would do this. Then you just divide through, and that would be your C. So that is how you find C. So the first step in any of these applications problems is to find K and C so that you can actually set up this equation. As I said, for the remaining cases, I'm not going to say much other than, again, if I am in the forced and damped case, this is the most general possible thing. I have m h double prime plus c h prime plus k h is equal to this forcing function. How do you solve that? How do you answer questions about it? Well, you solve it just like you solved every other non-homogeneous linear second-order constant coefficient equation. Okay. So that is that. All right, this is more or less all there is to say about these things. I could go into a little bit more detail with what are called phasors. Um, I'm going to hold off on that. I may kind of throw that into a kind of a combo like addenda lecture that I do when I talk about Green's functions. So I may kind of leave some of this straggling stuff to the side for now and talk about that, like I said, a little bit later. But for now, I think I've more or less said everything that I want to say about these applications problems. I encourage all of you to have a look at. I encourage all of you to have a look at the pictures in this chapter, in this section, because they do a good job of kind of explaining physically what it is that's going on here. If you are familiar with any of these types of situations from any other class, then me just telling you, oh, there are these cases like being overdamped, critically damped, or underdamped, that is like suggestive enough just from those descriptors to kind of tell you what's going on. But if you actually want to see the picture, I encourage you to actually look at those really nice graphs in that section. Okay. So anyway, I think that's more or less all I wanted to say for today. So as mentioned at the beginning of the lecture, there's no lecture on Monday, so your next lecture will be the following Tuesday. You're going to have your first midterm that I post later tonight, and it will be due, we'll say Monday at midnight or something like that. So anyway, that's the deal. So look forward to that, and I will see you all soon.